Hi guys, welcome to Ray Diagrams. So this is the third in a series of building block lessons, but this is the big one. This is the one where at GCSE, I haven't seen a GCSE question Ray Diagrams for a long time, but a fairly common occurrence at A level. You need to be able to demonstrate you have mathematical ability and drawing ability to determine the correct answer when given a variety of different lenses. So we'll start with the basics and then we'll move on from there. Okay, so step-by-step basis, this is no different to what you would have learned at GCSE. I probably would have got you to write this down, so if you've got your old notes out, there you go, cut and paste. If not, here you go, how to construct a ray diagram step by step. Step 1, draw a parallel ray to the lens. So we're talking about this ray up here, it needs to be parallel to the reference line. So that's obviously a confusing instruction if you're not sure. That's the reference line. We draw a parallel from our object. Now I'm going to make our object really obvious. I'm going to make our Christmas tree again. Fair enough. So it gets to our lens. Now in this instance, because the arrows are pointing up, we are dealing with a convex lens. Quite important. If this was a concave lens, this light would have travelled off in this direction. It wouldn't converge, sorry, it would be diverging. So we know it's refracted and it will travel through our focus point. So depending on the thickness of the lens, depends where this focus point is, and we just continue this line off forevermore, but it becomes irrelevant at some stage. Step 2, draw through the center. So from the top of our object, right from the top of our Christmas tree, so we've now got two lines coming from the same place. It goes through the center of our lens, okay, on the reference line, travels out the other side, and you'll notice straight away we've started to get some form of convergence. Step 3, we draw our third line from the top of our Christmas tree. So everything's been from the top of the Christmas tree. Now obviously light would be reflecting of all parts of the Christmas tree, and it all have different effects. But if we pick a particular reference point and the top makes the most sense, we'll be able to calculate everything we need. So this third line goes through the focal point on the object side of the lens. So we've got one going through the focus point on the non-object side, and one going through the focus point on the object side. It travels through that focus point and reaches the lens, at which point it travels perpendicular to the reference line. That's always one that people seem to draw strangely. All of a sudden we now have this lovely point here where we have a convergence. Now what we now need to do is, and I'm not sure if it happens on this slide or not, is draw in our Christmas tree. Now the bottom of the Christmas tree is on the reference line. It still is. The top of the Christmas tree is at the point they meet. So you'll probably notice straight away it's upside down. Okay, now so if I draw this relatively carefully, we're going to end up with, there's our third one, an inverted. And now, so I'll give you the list of what this is. So you either have it real, upright, or inverted. So you need these on your revision sheet so you can describe. So something is either inverted or upright. It is either magnified, or the one I always forget, diminished. Which in this case, you'll notice that the size of our two Christmas trees. This one over here is 4 units high, and this one is 2 units. So we would be, in this case, diminished. And now if it is either a virtual image, one that you can't actually project onto anything, or a real image, can be projected. Now by projected, it could be projected onto the back of the eyeball. It could be projected onto a wall. Okay, you can't project a virtual image, because you can't put anything between. So a virtual image would be between the object and the lens, which means that you couldn't possibly put anything between, because it would just block the light ray. So that is my 1, 2, 3 steps, and that is the same 3 steps for any convex lens, and even concave for a couple of parts. Okay, so now that I've taught you the 3 steps, here's a great question. It's identical in format. You go through the steps 1, 2, 3. I'll stop talking. You can pause it, I hope. I will go back to the start and don't let me start talking. And have a go at calculating image height, image distance, and describing, using those keywords from the previous slide, what that image is. But oh no! Oh man. Okay, so the second type of question you get with a convex lens is now our object is inside the focus point. Okay, so all of a sudden we can still do some of the steps, but we won't be able to do the third step where we would normally draw a line through the top through the focus point. It would have to be on this side to work. So what I'd like to do is first of all draw the first 2. So if in the next slide you'll get a blank version of this, but I will just so to the reference line, through the focal point and beyond. I think what I was actually trying to do before was see if I had a ruler, which I don't. Okay, then we would draw the second one. Now if I can do this accurately enough, you notice that I'm exaggerating it slightly. These are actually diverging. They're never going to meet, which is a bit of a problem, because as we know, to get a focus to see an image, they need to meet. So if they don't meet on this side, what we can actually do is go backwards along each line, and it's very important to be accurate when you do this, because you're only working with 2 lines. You don't get the confirmation of a third. Not that that's super accurate. There we go. And actually, where these 2 now meet, okay, and let's make this a Christmas tree, just so it's really obvious. Okay, we would now have a very big Christmas tree. Okay, now in the next one I'll let you actually do the correct calculations, but obviously you can use the keywords to describe this as well, and I think the answers appear in the next slide, but I'll go on to the next slide where you can have a go at this blank and see if you can actually calculate it. Okay, so this is the blank one, same as the one I just drew over. Have a go at it, see if you can calculate it, and the answer is on the following slide. Okay guys, so hopefully you've had a crack at drawing this out. I appreciate you don't have any grid paper at home, or if you do, good for you. Hopefully you found the following. So if you drew in the first ray, drew in the second ray, you now know they're not converging, they're diverging, so you have to go backwards. And if you go backwards quite a long way off this particular example, you should find that the image height is 40 centimeters. So just in case there's any confusion there at all, we're talking about the image being over here. Okay, nice big arrow. Image distance, 20 centimeters, or S, but this image distance is fine. Now the image of using those keywords we had earlier, magnified, because it's bigger, virtual, you could not display this on a wall, because you put a wall in between it ceases to exist, and it's upright, it's in the same orientation as the original object. So, how to construct a ray diagram that's concave. Now the best example I have of this is when you're looking through the viewer and a door. So you want to see a lot of what is outside, and you want a very small version of it so that you can obviously see everything that's going on inside just looking at one hole. So if you just drilled a hole through a door, you'd only actually literally be able to see quite a small part of the world, depending on how thick the door was, outside. If you use a concave lens, you're going to see all the light coming in from much greater angles. Yes, it'll make a smaller image here, but that's not what you're interested in. You're interested in being able to see everything going on outside. So, if again we've got our object inside the focal point, okay, and we follow our rules from before, first line goes in, we now know it's concave, so it'll go up, and we draw a second one through here, so there's number 1, so no different as before, except that we obviously recognize it's concave. There's ray number 2, they're diverging, so we need to then go backwards, and the only point that these two will meet going backwards is if we draw in this line here, therefore where they meet is where our new virtual image is. So the outside world will look very small, but the purpose of a concave lens is to bring a lot of light in from different directions, so we have an image that yes is smaller, but captures a lot more information going on outside. Okay, so this is magnification. So magnification of a lens can typically be either side of 1. So if it's less than 1, you're actually diminishing the object. If it's greater than 1, you're magnifying it. Now it's the image height divided by the object height. So V divided by U, and if you think back to Suvat, if you ever forget which one is which, the U in Suvat is the initial, and the V is final, as they're often known. So our initial object, and our final, the image it produces. So initial and final. Easy way of remembering it. Okay, so power of a lens. So lenses vary in power depending on how thick they are typically. The thicker they are, the shorter the focal length. Now, so power has a SI unit, the diopter. The focal length is, of course, in meters. That's very important. When you're dealing with ratio with lenses, it doesn't matter if you say in centimeters, as long as both the focal lengths you use are in centimeters. But if you want to convert to the proper SI unit, diopters, you need to use meters. Now, a convex lens will have a positive power. Now, to make that in really simple terms, here is our rays of light coming in. Here is your lovely magnifying glass with its biconvex lens, which means it's going to focus all the light down into a single point here, which I'm not going to try and draw it. If you're the ant, and this is a magnifying glass in the sun, you know that at this point you are one dead ant. That's meant to be a gravestone for an ant. Go with it. I feel like I need to label it now. So, positive power, okay, convex lenses, positive power, they're going to take all of this energy and they're going to focus it into one single point. That makes sense to us. If it's concave, it'll obviously do the opposite. It'll have a negative power. Okay, so you'll end up with a positive and negative power depending on which lens you're using. Right, something that comes up as a question in classes from time to time, and so I thought I'd chuck it in. I found this really good diagram on this is Google Images, and we talk about +4 and -4 lenses. So the capital D is diopters there. So if you need a +4 diopter lens, +4 power, there are various ways of achieving that. You could have, here is a +8 convex lens, and inside it, the other side, is a -4 concave. But we add them together, +8 +4 gives you +4. Or you have +6 -2 +4 0. Now the only thing that's obviously going to change in these three, so you've got the same power, but you'll have a different focus point, so depending on what the use of the lens is. Obviously, as you start to make the lenses more complicated, they're harder to make accurately, and you do get all sorts of strange effects chromatically around the edges. So good camera lenses that work this way are very, very expensive. Conversely, we can have -4 diopters, so we can have a +4 convex with a -8 concave, and vice versa, all the different options. But I thought it was a great diagram. I thought I'd include it, and it does go some way to explaining why everyone has different shaped glasses. Okay, so one of the things you're required to know, and I think I'll save some of the maths when we do multiple lenses for when we return, but as far as the spec is concerned, you just need to know that when we have biconvex lenses, thin, very thin, and that's probably the most important part here, they have to be thin and they have to be close. Okay, if they are thin and close, all we do is we add the powers up, so power of 1 plus power of 2 plus power of 3, etc. Which kind of makes sense if now I've drawn all over it. Let's do one at the bottom. So I've got my ray of light down the bottom, and it comes here, and we know that it's going to refract. It's going to go in here and then refract. And it's going to go in here and refract. And here is roughly our new focal point. Whereas if we just had this lens originally, the focal point is probably going to be, relatively poorly. There you go, somewhere over there. So I've now got all that energy coming in, all at a much closer focal point, which means I've also got any light now coming in at other angles is all going to be cumulative as well, not just light that's parallel. So the power keeps increasing. Now that's not technically how it all needs to work. Mathematically, we only deal with parallel inputs into lenses. So without convoluting it too much, all you need to know is when we're doing with thin, multiple lenses that are close together, we just add the powers up, +1, +2, +3, etc.